Hi. In this video, part of a series of videos where we're looking at how we're profiling various object detection and segmentation models on various different hardware platforms, we'll be looking at the i.MX 95 specifically. So to start, I just wanted to show this is a paper. It's on archive.org. Covering the i.MX EIQ Neutron and some optimizations they've done and how they come about this effective TOPS measurement. We'll skip down to page 9, where they have a table where they're measuring the latency of a few models. So we've got YOLO, V8, and segmentation, 8S and 8N detection. So we'll go run these benchmarks and see how our timing compares. So for the Neutron NPU, it's what's listed as Rs in this. So the latency they're reporting on the YOLO V8 Nano is about 24 milliseconds. So we'll start with that one first. So to start, I'm on an i.MX 95 Pro Neutron. In our benchmarking, I think the Neutron performance is about the same, whether you're on this board or an EVK or normal Freedom board. Two things we'll look at: throughput, latency. And we're doing a full COCO evaluation, so we'll show the end-to-end time, so from loading a JPEG from disk, decoding it into memory, doing the pre-processing, letterbox resize, so that the YOLO model can run inference on the input, producing the bounding boxes. It gets recorded into a Parquet file for ground truth analysis after the fact. And then for the segmentation models, there's the additional step of mask materialization, which again also gets written into that Parquet file for ground truth analysis after. We also record full tracing information, so we can get all the breakdown of all those stages in the pipeline, how much time they take, how they overlap when we do concurrent pipelines to increase the throughput, how the latency is affected by pipelining versus not. We can even drill deeper down to get specific layer-by-layer timing on the Neutron, which we'll also show at the end. So, yeah, with that, we'll start. One of the pieces, when comparing the throughput versus latency, we at Ozone have developed a DMA buff update for the Neutron driver. Basically, it allows the memory of the Neutron to be exposed as a DMA buffer using standard Linux DMA buffer API. And then our HAL library, so the EdgeFirst hardware abstraction layer, is able to map this and do things like have the GPU handle the pre-processing, so that letterbox resize and rendering directly into the NPU's input memory. Doing this can reduce the latency, but it does decrease the throughput currently, because currently the DMA buffers are limited to a single input output, so they can't be remapped as the pipeline's running, which means we can't do overlapping I/O. So we'll compare the two and show the trade-off between latency and throughput. So to start, I'll turn off the zero copy, and then I will start the profiler, and then we have a whole guide on how to use this. It's on the doc.edgefirst.ai. There's a link in the description. You can go look at it. But for now, we'll switch to the EdgeFirst Studio screen, and we'll go pick the COCO detection models, and then we'll start with the YOLO V8 Nano detection model like we saw in the paper. So again, the number here was 24 milliseconds for the nano model. So launch this. I'll pick the. So we've got a few ways of quantizing the model. We'll focus on this with the smart quantizer. We've got another video that talks about the smart quantizer, how it works. It's actually also covering the i.MX 95 because the smart quantizer has a very interesting interplay with what actually ends up running on the Neutron NPU. But that's a whole topic on its own, so there's a link, or I'll add a link to that video, and you can watch it. So now we'll go run the smart profiler, validate, yeah, default runtime, which since this is a Neutron model, it'll run the Neutron delegate. So that was it, downloading the model. Now it's doing the warm-up, so loading the model, running a few inference runs, takes about 8.3 seconds, and now we are running. So first we can see the FPS is at about 77, 78 milliseconds. The latency of inference, 50 milliseconds. So that's obviously higher than that 25 millisecond, but we're running 4 concurrent pipelines together. So what this means is by doing the overlapping I/O, we're able to get much higher throughput, but at the cost of latency. So if your application is more throughput sensitive, then you can run the model with a high level of concurrency. So in this case, every stage in the pipeline from capture. So capture here is reading loading a JPEG from disk, doing the JPEG decoding. Pre-process is the letterbox resize. Model, then you do inference, and then model decode is handling the decoding of the bounding boxes into uniform normalized boxes that we then write to this Parquet file over here. That gets uploaded into Studio where we do the ground truth analysis. The trace file, we'll look at that. We can go inspect the tracing information in detail to see what the exact breakdown was. So the metric here, we're showing the latency of it. So as you add deeper pipeline, you increase the latency. So before we look at the lower latency zero copy version, we'll go pull this up in Studio. So if I go under Cocoa detection here, under the YOLO V8, and then that's this session here that we just ran. So we can see the host i.MX, see the host i.MX 95, Freedom Pro board, the kernel version, and whatnot. If we look at the charts, we can see the MAP for this model, 34.5. So if we were to compare this, actually we can go do that very quickly here, compare it to a float model. For example, this here was run on Coramel on the CPU on a Mac. So this matches the published numbers you would get from Ultralytics. So this is 43% MAP. No, that's not right. This is the small model. Yeah, small. So if we look at the nano model charts, there we go, that's the right number. So 35.8% MAP. And then if we go back and look at what we just did with the i.MX 95, so this is a quantized model, we see the 34.5. So we lost about a percentage point to quantization, but that's pretty good. And then, and again, if you look at our other video about the smart quantizer, you'll see this is probably a lot better than you typically get when you quantize this type of model. And then we've got lots of charts about CPU utilization and power and all that, but we'll look at the FPS so we can see our throughput over time. And on average, we're at about 78%. We peaked out at about 79%. And then for our latency, I guess there were a few spikes here, but typically the inference latency was at 48, which is what we were seeing in the profiler. Now, if we click the profile button, we can actually go see for an individual stage. So not the latency where we're accounting for that deep pipelining, but we can actually go look at the effectively the instantaneous time. So if I stretch this out, this has all 5,000 samples from Coco, so it's quite a bit in here. So first thing, the profiler breaks it down. So we've got our different slots here. These are synchronization points for the NPU. We've got the, we can see the decoder thread here. So this is what's handling the box decoding. You'll see they're kind of different sizes. The more candidates that are produced, the longer it takes to decode. This is being run. It's a standard Coco evaluation. So we're running the model with a 0.01 threshold, so it produces a lot of candidates. So this decoding time on a normal deployment, we're using, say, 0.25 or even 0.5 threshold. These times come down probably by about 10 times. So from about 10 milliseconds, they'll come down to about a millisecond. Then we've got the model. This is just sort of showing the higher level of the model decoder. The pre-processing time, so this is the CPU resize with letterbox. It handles reading from the JPEG output. So this can actually use, if we look at image load, you'll see it's using the Video for Linux codec, so the i.MX 95 as a hardware JPEG decoder. We run this across 4 threads, so the decoder is always busy decoding some JPEG. It generates NV12 output, and then the preprocessor can read the NV12 output directly to generate the RGB, packed RGB with letterbox resize and the gray bars on the top and bottom. So that all shows up here. And then if we go down to look at the actual invoke time, now this model was generated without the NPU graph breakdown. So when we look at it, we just see the invoke time. But we see this is that overlapping invoke. So as I mentioned, it takes that 44 milliseconds, but they're running all overlap. So in each of those 44 milliseconds, there's up to 4 invocations running at the same time. So we're getting really high throughput, but at the cost of some latency. This is all configurable. You can force it to use a single slot with or without the DMA enabled if you want to reduce your latency. It's all very configurable. So we'll go look at the zero copy, but before, what I'll do is I'll trigger a quick conversion. So go to the training session here, artifacts, and then we've got the Neutron converter. So what I'm going to do is do the smart quantize conversion, and I'm going to enable the NPU profiling. So when we run the profiler on this model, it'll show us the layer by layer breakdown. So we'll go ahead and start that. And then we can go back here to our validation sessions, and while it converts, we'll go back to the profiler over here and run with zero copy enabled. So I just change that environment variable, run it again, go back to the studio screen. I'll pick that same YOLO V8 Nano model again, running the i.MX 95 smart quantized version. There we go. Now the throughput is down to about 55 frames per second, with the latency down to about about 40 or about 50, sorry, milliseconds of latency. The inference latency itself, so we can see the concurrency that now is capped at 1x. So with DMA enabled currently, concurrency gets capped at 1. But you can see that 13 milliseconds of latency is obviously, well, it's nearly half of what we see in this paper here, the 24. And then the model decode, well, that's gone up a little bit, and we'll see why in a moment. Capture, well, should be about the same. I don't remember exactly, but we can go look at it in the profiler once this finishes. So it'll take a little bit longer to complete. Do that, quickly take a look at how our, so we can see the progress here of that validation session. I'm quickly going to look at how our conversion session, okay, that's still pending, no, pending, okay. So now that finished, it uploaded the results to the server. So if we swap back here, we'll see this takes a few seconds to refresh, but there we go. It's running the analysis now. So that's comparing the metrics, so the bounding boxes, how they overlap with the ground truth to generate MAP, precision recall graphs, and all of that. Now it's done. So again, you can see same target, same model. Sorry. And then when we look at the charts, so the MAP of this model is still that same 34, roughly and a half. And then the FPS, so that dropped down to about 54. If we look at the average, okay, so 55, pretty much across the board, it's pretty stable. And then our latency per stage, so capture is about 8 milliseconds, pre-process 13. So again, those are still pipelined, but inference is now limited to a single worker. So now that's down to that 13 milliseconds. So if we go look again at the detailed profiler, see again the image load is running concurrently. There's some overlapping I/O, same with the decoder, post-processing, but the invoke Neutron delegate there is serialized. So 1, 1, 1, 1, 1. So it's all running these back to back. And we can see here the actual time for invoke is that 12 milliseconds. The reason for the slightly higher timing there is, well, there is I/O time in between. No, there isn't. This is the DMA version. I'm getting ahead of myself. I couldn't tell you exactly what the difference is. I guess it's waiting. Right. So because there's a single buffer, we can't actually do the GL rendering overlapped. We need to wait until we have access to that shared DMA input buffer. So that render step happens before all these before these inferences. So there's still overlapping pre-processing, but the final part of it, the final render, that needs the that target input tensor. We only have the one because we've serialized the Neutron to enable the DMA. So that's what this gap between inferences comes down to. So as we saw, we cut down the latency in about half We still have really, really good throughput, so 50 some frames per second on this two tops, two effective tops. I don't know how you measure tops. Regardless, 50 frames per second for YOLO V8 Nano is really good at that rating. And then with stacking concurrency, we take a hit on the latency, basically by 2x. So we're at about 100 milliseconds of latency now from the time. Keep in mind, this is loading a JPEG from disk, decoding it, running through, getting the bounding box results. So that's still a pretty, fast part. But that 100 milliseconds of latency, the trade-off is we boost our throughput by about 50%, getting into the high 70 frames per second. And if you crank up the power saving and all that to the max, make sure you got a good heatsink installed, but you can get this thing up into, I think we can get pretty close to 90 frames per second with that same roughly 100 milliseconds of latency. Speaking of heat, we do capture that, so you can see our temperature over time while running this. Where is it? CPU utilization. Okay, I lied. We don't have a chart for heat, but as you saw in the profiler, we do capture it here. So, okay, that's not so bad. 55 degrees Celsius. So, anyways, there you have it. Running the YOLO V8 Nano at roughly 50, a little over 50 frames per second, as well as close to 80 frames per second. And the trade-off, switch an environment variable between zero copy, no zero copy, and basically you're just trading throughput for latency. So if you need lower latency, for now, turn off the DMA, and then, turn on the DMA. If you need more throughput, turn off the DMA and you'll get the high frames per second. Do expect to be able to support overlapping I/O with DMA in the future. We can do that, for example, on the Era 240 NPU, as well as other processors. So it's just a quirk to this new part that we're still working out. That's it for this video. Thank you.